Okay, we're back to talk more about soil colloids. Remember, these are these tiny 2 micron or smaller fraction of the soil that has this enormous surface area. And this is where all the different kinds of chemical reactions are happening in the soil. And remember, these chemicals that are moving around in the soil are primarily nutrients for plants and other kinds of organisms that live inside the soil. So this is where a lot of the real soil activity is taking place. So let me share my screen again. Let's go up here. Okay, so again, chapter 8, and we kind of focused on the first section of chapter 8 in the last video, and now we're going to focus on kind of an abbreviated version of sections 8.6 through 8.9. Okay, so we said that these soil colloids, these small fragments that have lots of surface area, often have charges. So they'll have a positive or more commonly a negative charge. And it's that charge that allows them to bond onto either water molecules or other kinds of ions in the soil. And so this process is called what creates these negative charges is a process that's called isomorphous substitution. So iso means the same, morphous means like the same shape. So what happens is in the general mineral structure that creates originally the parent materials that break down to form the rocks, they have, general chemical structures where maybe there'd be a bunch of silica and then there'd be a bunch of aluminum. And then on occasion, what happens is something like an aluminum will be replaced by something like magnesium. And aluminum and magnesium are similar, so that's why we call them isomorphous. We can substitute one for the other. They're a similar size and shape. However, they actually have a different charge. So aluminum has a 3+ charge, and in kind of the normal structure of this particular mineral that we can kind of see up super close on the left, we would have these different oxygens and these different aluminum ions or atoms bonded together, and they would be balancing charges. However, when we replace the aluminum with the magnesium, all of a sudden we don't have as much positive charge as we did in the original structure. So now this isomorphous substitution has resulted in only 5 positive charges balanced with 6 negative charges. So now we have a net negative charge as a result of this isomorphous substitution. And this is really common. Aluminum is one of the more common elements in different kinds of mineral structures, and then aluminum is commonly replaced with other fairly common elements like magnesium or calcium to create these net negative charges in different kinds of mineral compounds. So as I said, having that aluminum 3+ replaced with a magnesium 2+ charge or calcium 2+ charge is the kind of thing that results in all these negative charges spread out throughout the soil. In the case of organics, because we said some colloidal material is organic, not all mineral. Why is this changing to the next slide? A common source of the charges are different kinds of organic acids or different kinds of what are called hydroxyl groups. So water, I think most of us know, is made up of hydrogen or 2 hydrogen atoms and 1 oxygen atom, H2O. And sometimes water will dissociate. And so the 1 hydrogen atom will break apart and then leave a group of 1 oxygen and 1 hydrogen together. That's called an OH group. And we see a lot of these OH groups in organic acid, so like humic or fluvic acids that give like the dark brown color to like organic matter rich soil. And that OH group has a negative charge. So that's the kind of thing that would result in having a charge on an organic material in the soil. So there are some instances where we have positive charges as well, and we're not going to get like much more in depth into the chemistry to explain all the different kinds of options. But the more dominant, common kind of thing that we see is that most colloidal surfaces have these negative charges. And so they're particularly good at bonding onto things that have a positive charge. So nutrients that are like magnesium, like calcium, that have a positive charge can be held and exchanged well. And nutrients that have negative charges, which would be things like nitrate groups with nitrogen or phosphate groups with phosphorus, sulfate groups with sulfur, those things might be more difficult for the soil to hold on to with these kind of pure colloidal magnets, essentially. Okay, so when we're kind of imagining how these different ions are being kind of bonded on and off these negatively charged surfaces, we want to kind of imagine what this looks like up close. So on the left, I have a diagram that's from your book that we looked at in the last slide. And so it shows that we have kind of external clay surfaces, and then the clay, right, is made up of all these sheets. So then we have these kind of internal little slits in between the sheets where there's additional surface area. And again, primarily these surfaces have negative charges. So there's all these little dash negatives all around the surface of these things. And so you can see that there's all these elements, which we could think of as primarily nutrients, that are kind of swarming around, being attracted towards the soil surface by these negative charges. And you can see that mostly these things that are swarming around the soil surface have positive charges, because the negatively charged surfaces are attracting positively charged things. There's only a handful of elements that have negative charges, a couple chlorines. I see a sulfate group, a sulfur and oxygen group, and those are not tightly held into the soil surface. They're just kind of floating by. And so these positively charged elements, things like Ca calcium, Mg magnesium, K is potassium, etc., sodium, Na is sodium. So they are kind of bonding on to these negatively charged surfaces, both on the external surfaces and on the internal surfaces. And they are constantly exchanging. So you can see on the bottom part of this diagram, there's calcium and magnesium that are circled, and it says cation exchange. And so you can kind of imagine this like a little swarm of bees, where bees are constantly coming and going. And as one bee just happens to kind of get a little bit closer as it's kind of buzzing and vibrating around, it can kind of get right into the center of the swarm, and then another one will take off as it vibrates. It ends up being just a little bit slightly farther away from the negative surface at that moment. They'll exchange, and then all these things are constantly in motion. They're not still, they're all vibrating around. And so as they're vibrating, other elements that are kind of floating through the area might for a moment end up being a little bit closer than another element, and then we would have an exchange, an exchange, an exchange. So they're constantly, all these things are coming and going, vibrating around. And I think a swarm of bees is a common analogy I've heard, and it helps me kind of visualize what's going on here. So that's good, because we want elements to be held in the soil. We don't want them to all just be washed out, but we also want them to be held not so tightly to the soil that they're not available to plants. So if there's this constant exchange going on, that means that they're there in the soil, but also going to be available to organisms and plants that are trying to access them. So there's a little bit of a difference usually in how strongly these different kinds of ions are held onto the soil, depending on whether they're bonded to the outer sphere areas or the inner sphere areas. So again, this same diagram we saw on the last page on the top shows kind of the outer areas as opposed to internal surfaces. And then on the bottom, we have a picture of these silicate clays with outer surfaces and then inner surfaces in between the sheets. And one thing that's not really shown in this image on the top is that there's, in addition, a film of water that's also being attracted to the charge on the soil surface. And so there's lots of water, especially in a soil that has adequate water, that's kind of surrounding and bonded to all these soil surfaces as well. And that is particularly true on the external surfaces of the soil colloids. And so the water that's bonded onto the soil surface is acting like a little bit of a buffer that's blocking some of the charge that's holding these ions onto the soil. So the water is essentially kind of weakening the force with which the ions are held to the outer colloid surfaces. And that means that those ions are more exchangeable. So they are being still pulled into the charge from the soil colloids, but they're going to be more available to move around, to exchange, and then be available for plants in this kind of soil water solution outside the soil colloid. Whereas on the inner sphere, the water film is not as predominant. It's not as like completely coating the internal surfaces. And so the ions are more strongly bonded. And those ions then are a little bit harder for plants to get at and other organisms to get at. Although microbes that are smaller have an easier time kind of accessing things that are on these inner sphere surfaces. Plants tend to have a harder time, as far as we understand, accessing these ions and nutrients that are very closely bonded on the inner surface. Okay, so as we already mentioned, all these different cations, positively charged atoms, many of which again are nutrients, things like calcium or magnesium, sodium, and they are constantly vibrating around. They're on the outer surface because of a film of water loosely held on to the soil colloid surface. And as they vibrate around, they might, for microseconds, be slightly farther away from the colloid surface than another cation that is kind of cruising by, moving through just randomly in the soil solution. And at that moment, as these two elements are randomly vibrating around, one might get close enough to the other to exchange it, just like bees coming and going from the swarm. And that, again, is what we refer to as cation exchange. So commonly, a measurement that you hear about in the soil is a soil's CEC, as it's abbreviated, or its cation exchange capacity. And what this is supposed to get at is kind of how many nutrients are around the soil that are not held so tightly that they wouldn't be available to plants, that would be kind of extractable by plants as they're constantly being moved around and exchanged on the soil colloid external, in particular, surface. And so the way that this is usually measured is how much positive charge can be held per mass of soil. So how much capacity does that soil have to bond on to these different positively charged ions? And the way that this is measured in practice is that we take the soil and then we use some sort of chemical extractant, so something like ammonium acetate. And if we were in person, we could do this in the lab, but we would put this kind of solution on the soil, and the ammonium acetate would bond onto the soil surface and block these cations from doing the same. So the cations would essentially get expelled from the soil surface, and then they would be floating around in the solution, and then we could measure the concentration of the different kinds of cations in the soil to see how many had been on the soil surface. And then again, that should tell us in the environment how many of those ions would have been available for plants to get at and use as nutrients. So the cation exchange that we would expect to see from a soil is going to depend on the kind of soil. And not surprisingly, the higher the colloid content in the soil, which is going to mean the higher the surface area in the soil, the higher the cation exchange capacity, or CEC, is going to be. So things like clay, or things that have lots of this humic matter, this humus, like histosols, are going to have really high cation exchange capacity. And then kind of intermediate loams or vertisols or compost would have more of a medium cation exchange capacity. And then soils that have the very lowest surface area of all, something like a sand, would have a very low cation exchange capacity. So not surprisingly, it's difficult to grow a lot of things in pure sand, right? There's just not a lot of nutrient and water holding capacity in that sand. On the other hand, if you're trying to grow something in pure clay, there might be a lot of nutrients there, but they're going to be bonded really tightly onto the soil surfaces. And so it might be hard for plants to get them. And so a lot of times this kind of in-between material is really what's ideal for plant growth. So kind of one more concept that I want to introduce is another measurement that's often reported in soil testing, which is called base saturation. So cation exchange capacity tells us how many different cations are able to be held by the soil, but not all cations are actually the same. So cations like calcium and magnesium that have a 2+ charge, or potassium, which is K, or sodium, Na, which is sodium, they behave a little bit differently in the soil than aluminum, which has a 3+ charge, and hydrogen, which is just kind of a unique case, even though it has a 1+ charge. So cations that are in the first group that I listed, calcium, magnesium, potassium, and sodium, are called base cations because they tend to balance out and actually minimize the number of hydrogen ions that are in the soil. And as you may or may not know, how acidic something is essentially a measure of how many hydrogen ions are in the soil. So where we have lots of calcium, magnesium, potassium, and sodium occupying negatively charged space, we may have less hydrogen ions, okay? So we would have basic soil conditions or alkaline soil conditions as opposed to acidic soil conditions. On the other hand, if we have lots of hydrogen, then by definition, we have soil that's quite acid. And then also aluminum, which has a 3+ charge, actually has the ability to interact in different chemical reactions that can break apart water and actually create more hydrogen ions. So where we have aluminum, we're going to have more hydrogen. Those things often go hand in hand. And so when these cations are present, we're going to have soil acid conditions. And soil acidity, as we'll talk more about next week, has a big impact on the availability of different nutrients in the soil. And different plants have different nutrient requirements. And so different plants do better in different soil, parts of the soil pH or acidity spectrum. So certain things like berries or like rhododendrons, azaleas, like acid soil. And so they might do better with a little bit of aluminum or hydrogen in it. Other kinds of crops are going to need a more neutral pH or leaning towards a more basic pH. And so we might also have an interest in trying to understand the base saturation of cations in the soil. And we could measure that in a similar way that we would measure the cation exchange capacity by kind of just stripping all the different cations off the soil surface with some sort of extractant. But in that case, then we would only be trying to measure the base cations in the soil solution. So anyway, that's another common soil measurement that you might come across. And so I just want to kind of explain to you what it means. And one thing that you can do to change your pH and then your base saturation and also your cation exchange capacity in the soil would be adding lime, agricultural lime, and that can actually increase your cation exchange capacity and reduce the acidity of your soil. So make your soil less acid or more basic. And again, we're going to talk more about soil pH next week. Okay, that's all I have for this topic.